Hi, thank you for watching my video. I'm Juan from UCLA, and I'm presenting my work on robust reinforcement learning against adversarial attacks. This is a joint work with my collaborators from MIT, University of Michigan, and UIUC. In reinforcement learning, we have an agent which interacts with the environment. The agent observes the current state of the environment and takes a corresponding action. The environment moves to the next state given the current state and the action taken, and gives the agent a reward. The goal of reinforcement learning is to find an agent policy that maximizes the cumulative reward from the environment. Reinforcement learning, especially when a deep neural network is used, has achieved great success on many tasks, including playing Atari games where the neural network receives a game screen as an input and predicts the next action in discrete space, and robotic control tasks where the neural network receives current system status such as position and velocity as the inputs and predicts the actions on actuators. The robustness of reinforcement learning can be considered in many aspects. When the agent observes the current state, its observation can be perturbed and different from the true environment states. Also, the agent's action, the environment dynamics, and the reward signal can also be perturbed. In this work, we consider the case where the observations of the agent can be perturbed. Researchers show that adding a small adversarial noise to state observations can successfully attack agents trained using different RL algorithms for many tasks. The agents can easily be fooled and receive a very low reward. For robotics tasks, the attacks can easily make the agent fail. For game playing such as DQN Pong, the attack can make the agent miss the ball every time. All these attacks follow the same setting of perturbing state observations, where the attacker adds a small adversarial noise to agent observations. The agents typically need to observe the environment state from sensors, and the sensors can contain natural or adversarial noise. The perturbed observations lead to wrong or suboptimal actions. For example, in this car navigation scenario, here the green icon is the true position of the car, and the red icon is the observed position under uncertainty. The uncertainty can come from an inaccurate GPS signal. If the policy is not robust to the noise in the observation, the car may turn left too early and crash into the wall. In this work, we want to learn a robust policy which is able to achieve high reward even when a strong adversary perturbing observations. Previous works mostly focused on empirical attacks and little theoretical understanding was made. Obtaining a robust RL agent is more challenging than a supervised learning setting because there is no ground truth action in reinforcement learning. One approach is to borrow adversarial training from supervised learning to reinforcement learning. Several works apply techniques similar to adversarial training, but these approaches are ineffective. Here we show that training DDPG agents under previously proposed adversarial attacks. They may damage agent performance, and the agent still remain vulnerable to stronger attacks. In fact, without a theoretical framework under this setting, it is unclear what is the right approach to conduct adversarial training, and the adversarial attacks proposed by existing works are not strong enough. In our work, we first develop a theoretical framework called State-Adversarial MDP or SA-MDP to characterize the setting of perturbed state observations. In SA-MDP, the adversary knew as a worst-case bounded perturbation to the agent's state observations, but does not change the true state where the agent is located. Compared to a regular MDP, we have an additional element, which is the perturbation set Bs. We assume that given a state S, the bounded perturbation is within a set Bs. For example, we can assume the neighborhood Bs is a L-infinity ball around the original state S. We can naturally define the value functions tilde v and action value functions tell the Q of a given agent under a fixed policy pi and a fixed adversary nu. As in regular MDPs, the value functions are defined as an expectation of discounted cumulative reward. Our SA-MDP characterizes the worst-case adversarial perturbation on state observations, so the adversary always minimizes the agent's expected reward by generating any valid perturbations. Then, our goal in SA-MDP is to find an optimal policy pi star under the optimal adversary nu star, which is the max-min problem. Here we show a toy environment with 3 states and 2 actions. The optimal policy of regular MDP is to take action A2 at state S1 and take action A1 at state S2 and S3. We get a maximal value of 100 for every state. However, in SA-MDP, an optimal adversary can perturb S1 to S2 and perturb S2 and S3 to S1, which misleads the agents to take wrong actions at each state. The optimal MDP policy I just mentioned will receive 0 rewards in all states in SA-MDP. SA-MDP has some interesting properties. Unlike MDP, we show that a stochastic policy can sometimes be better than any deterministic policy in a SA-MDP. Most importantly, a Markovian optimal policy does not necessarily exist, even for very simple SA-MDPs. So, it can be hard to find the optimal policy for SA-MDPs. Although it is hard to directly solve the optimal policy, we show 2 effective and orthogonal approaches to find a robust policy under attacks. We now go over the first approach, State-Adversarial regularization. We first prove that if we can bound the distance between the action distribution under the original state observation and the action distribution under the perturbed observation, the maximum performance loss caused by the adversary in SA-MDP can be bounded by a constant factor alpha. Intuitively, the theorem says that a policy not sensitive to state perturbations can be robust under adversary. We want to map 2 states S and hat S close to each other to 2 actions that are also close to each other. This inspires us to use a regularizer to improve robustness under adversarial attacks, which in general requires us to solve a minimax problem to find a policy that has small max divergence under state perturbations. We want to find the parameter theta, which minimizes the worst-case divergence on the adversary. Now, let's see how well this approach works in practice. In experiments, we include time environments for both in Mojuku control tasks and Atari games to apply our regularizer to 3 popular deep learning algorithms, PPO, DDPG, and DQN. We use 2 different approaches, convex relaxations of neural networks and SGLD, to solve our Minimax regularizer. For PPO and DDPG agents, we use 5 different attacks, including 3 new strong attacks proposed by us, and take the lowest average episode reward as our final evaluation metric. To ensure reproducibility, we run each setting multiple times and report the median rewards. For PPO and DDPG agents in continuous control tasks, the states are a vector of system position, angle, and velocity, and we add L-infinity bounded perturbations to normalize the states. Our agents significantly outperforms other baselines and remains robust under strong attacks. Both the convex relaxation-based and the SGLD-based solvers are effective. On the right, we show videos of humanoid and ant environments. The vanilla agents can barely stand up, while our robust agents can successfully walk a long way. For DQN, the states are 84 by 84 image pixels, and we add L-infinity norm bounded noise to the pixels. Our methods outperform existing works using adversarial training and robust imitation learning in most settings, sometimes by a large margin. The video is for Atari Roadrunner environment, where SA-DQN achieves near-perfect scores where vanilla DQN gets 0 points under attacks. Now, we discuss our second approach of using an empirical minimax optimization to find a robust policy. Intuitively, we can first find the optimal adversary nu under the current policy pi, and then find the optimal policy pi under a fixed nu. We can then alternate the two steps in a similar manner as in adversarial training for supervised learning. We show that when the policy is fixed, finding an optimal adversary is equivalent to solving an optimal policy in an MDP by treating the agent as a part of the environment. The adversary sees the agent and the environment as a whole, and this equivalent environment is still a MDP. This allows us to use any reinforcement learning algorithm to find the optimal solution for this equivalent environment, leading to an optimal adversarial attack. We use deep reinforcement learning to learn this optimal adversary. We code optimal here in the deep learning setting because when deep learning is used, it does not necessarily converge to the optimal solution, but practically it still produces very strong adversaries. Here we show two scenarios where existing strong attacks, such as the robust sarsa attack, can make an agent fail to move and receive small positive rewards. But our optimal attacks, under the same perturbation budget, can lead the agent into moving to the opposite direction, receiving large negative rewards. Next, we show that when they fix the adversary, the learning problem of the agent becomes a partially observable MDP by treating the adversary as part of an environment. The agent sees the adversary and the environment as a whole, and this equivalent environment is a PO-MDP. Solving a PO-MDP typically requires history-dependent policies, and it is much harder to find the optimal policy unless the problem is very small. Practically, we use a LCM-based policy network to utilize history information and use policy gradient to optimize its parameters. Finally, we propose our alternating training with a learned adversary framework, ATLA. In ATLA, we alternatively optimize the agent and the adversary using any deep reinforcement learning algorithm. We will use PPO for both the agent and the adversary in our experiments. In experiments, we compare our ATLA training procedure to SA-PPO, our state-adversarial regularizers, and also evaluate the combination of the two. We also compare to existing adversarial training-based approach without using a learned optimal adversary. We show that the existing adversarial training method is not effective under strong adversaries because they use a relatively weak attack for adversarial training. Our ATLA framework is based on learning an optimal and the strongest possible adversary during training, and is much more robust than vanilla agents and existing adversarial training-based approach. We also find that the LCM-based policy can be helpful for defending adversarial attacks, because our theory shows that the learning problem for the agent is essentially a PO-MDP under a fixed adversary. So history information are helpful here. By combining our ATLA and the state-adversarial regularizer, we obtain the most robust agents. To summarize, we propose two orthogonal approaches based on our SA-MDP framework to improve the robustness of a RL agent on the adversarial attacks on state observations. The first approach is based on a state-adversarial regularizer on agent policy. The second approach is based on alternating training with learned optimal adversaries. The two approaches can be combined together to obtain a very robust agent. I list all relevant papers regarding my video here. The main SA-MDP framework was proposed in my new RIPS paper in 2020. Thank you again for watching my video. Please check out our code and pre-trained agents on GitHub. If you have any questions regarding our work, feel free to send me an email. Thanks.